record button. Okay, so now everybody should see a little red dot on the top left hand of their screen, flashing dot, which indicates we're recording. And with that quick bit of housekeeping, let me hand over the presentation to the Bioprinter team, Group 7.
Duke, you can take it away.
Oh, we're starting right now? Okay, so hello everyone. Thank you for coming to our Zoom presentation. We are Under Pressure. Our team consists of 6 members, Christopher, William, Jack, Amir, Ryan, and then me, Duke.
All right, so here we have our mind map for our project. Basically what this is showing is how customer requirements affected certain subsystems and how well we then met those requirements with our final design. So if you go left to right, on the far left, you have all customer needs, which were laid out by the customer. Next over is how we translated those customer needs in quantitative metrics. And then you have the arrows, which are showing which subsystems were affected by these metrics. And then finally, on the far right, you have how well our design met all of those individual metrics.
So 3D bioprinters are becoming common around the world. Many research and development laboratories have these machines. Unfortunately, these bioprinters are expensive and not many are mountable to a microscope. So we were tasked by the UF Soft Matter engineering group to develop a bioprinter that could print while mounted to a Nikon Eclipse TI microscope. The printer needed to have the capability to print complex cell structures into a 96 well plate that held LLS. The printer also needed to be repeatable, dependable, and sturdy, while being commercially viable for any school, university to buy these printers. And to achieve these set goals, we focused on cost effectiveness and simplicity. And we kept the design under $4,000 by mainly using off-the-shelf parts or OTS parts, and to keep the design simple enough to have lab technician to repair and maintain these parts without requiring high technical knowledge.
So moving on to an overview of the print head. A few key features of the print head itself. So we use a modified OTS mounting solution, some simple linear rails with polymer bushings and center driving pistons. And then as well as the extrusion method itself uses a 18 gauge off the shelf needle connected with a lure lock to bar plumbing adapter. And then not pictured is it is then piped to the dispensing mechanism using a biocompatible fluid. So the way that the printing would actually work is in the 96 well plate, the bio fluid would be picked up from one of the wells and then moved over to the wells where the experiment will be conducted. So taking a look at the modified OTS mounting. So to keep with cost effectiveness and simplicity, we opted for an OTS condenser port adapter. So what actually condenses, or what connects the print head to the microscope and holds the dispensing structure. The off-the-shelf part was extremely heavy, 181 grams estimated, which is almost the entirety of our 200 gram weight budget. So we went ahead to modify it and reduce weight, so we were able to cut it down from 181 grams down to 37 grams. As well as doing that, that allows us to control some of the more critical features. So the OTS part, the intention for the design was to hold apertures to adjust the light levels coming into the microscope. So none of the dimensions on the OTS part, aside from the dovetail, are that critical. So by us modifying them, we're able to control the positional location of the holes which the Z-rails mount to, as well as the perpendicularity of them. So moving on to the guide rails, we use 1/8" stainless steel support rails, and they're held onto the stationary carriages with a line fit to a light press and are constrained axially by the C-clips. For the bushing material, we went with an acetyl copolymer bushing. We were originally considering a PTFE Teflon bushing due to its low coefficient of friction. However, upon further research, we found that the nylon was poor at dimensional stability, as well as was subject to high wear. So acetyl copolymer was the next best option there. And some of the benefits, aside from the low wear, is it's more machinable, dimensionally stable, so that ultimately we exchange the low coefficient of friction to the longer life of the component. So moving on to the center driving pistons. So the X, Y, and Z motion is controlled by hydraulic pistons. And the X and Y features the piston, which is located between the two guide rails. So by doing this, we're able to balance any potential moments by the pushing of the piston and reduces the risk of racking. So it ultimately increases the smoothness of motion. The pistons are custom manufactured and are driven hydraulically using water as the fluid, so that we're able to operate in the BSL-1 clean room lab. So the hydraulics is driven off-site on the dispensing / driving system, and are connected to this assembly here on the right using a barbed fitting.
So now we're going to go over an overview of the design and driving system that we have, which you can see on the screen right here. So some highlights about the system are we designed it to have a modular piston system. We also designed a smoothie board mount for it so that we can mount all of the electronics, the smoothie board included inside of the enclosure. And then finally, we designed a sheet metal enclosure around the driving system and the electronics in order to protect them. So on the screen right now, you can see the modular piston system that we designed. So a really key thing was we wanted to limit the amount of parts that we would have to manufacture for the print design. So therefore, we chose to go with a modular piston system that we could simply make one full set of parts, and then all we had to do was replicate the parts in order to drive each of the axes as well as the dispensing system. So XYZ as well as the dispensing system are all driven with an individual glass syringe and linear actuator assembly. And the assembly allows for the quick changing of the glass syringe should you need to increase your resolution, or for some reason if the glass syringe were to break, it would allow for the syringe to be replaced very easily. So on the screen right now, you can see the smoothie board mount that we designed. The smoothie board mount was designed to be printed out of 3D printed using ABS and then have brass inserts pressed into it. This allows for very cheap manufacturing as well as quick assembly. This mount essentially allows for the smoothie board to be placed inside the mounting box on the DIN rail that we mounted inside of it. And then finally, we have the driving system enclosure. So the driving system enclosure we designed in order to protect all the electronics that we have inside, as well as the glass syringes and the driving system. On the front of it, on the front of the box, you can see that we wrote PUP, the printer name. And that's not just there for the name. We're actually using that to draw air into the box and then out through the two exhaust fans we have in the rear in order to cool the box. In addition to that, you can also see that we have rubber grommets in order to protect the hydraulic lines that we're going to be running to the actual print head.
Okay, so now we'll dive into some of the critical analyses we performed on our final design. First among which we started with the motion we would be able to achieve in X and Y using our pistons, hydraulically driven pistons. So with the actuators that we're using in this design, we have a max velocity with those of 25 millimeters per second with no load. To account for the loading that they would see, we decided to implement 75% of that as what our speed with load would be. So that gave us 19 millimeters per second. And then using the ratio of the pistons in the motion system, which were from the syringe piston to the custom pistons on the print head, this led to us having a needle velocity in X or Y of 14.5 millimeters per second. And from previous research, using this value as well as the flow rate we would be implementing to dispense the fluid, we would be able to find our printable feature sizes. So by using a flow rate of 1 microliter per second and this needle tip velocity, we would be able to print feature sizes around 0.3 millimeters. And this was at the top of our range of desired feature sizes. In order to reach the lower end of our range, which would be around 15 micrometers, we would simply lower our flow rate. Then to further ensure that we could achieve this flow rate with the actuators, since these actuators are also doing dispensing, we needed to perform another analysis. So to determine this force required, we apply the Bernoulli equation, observing the flow along a streamline within the dispensing flow line. So starting with position 1 being the syringe piston and 2 being the outlet of the needle. Using the needle outlet allowed us to imply a few assumptions, which simplified the equation, along with the syringe area being a lot larger than the area of the needle. And then from there, we were able to solve for the required force, which ended up being just based on our areas, the density of the fluid that we were using, and then the difference in height between the control box and the print head. And we found this required force to be 0.0073 newtons, which is well within the achievable range of the actuators.
So going on to some of the calculations that we performed on our driving system, one of the most important things that we were looking for was we wanted to make sure that the positional tolerance of our print heads was within the supply dimensions provided by the customer, which was 1 cell diameter, which we estimated to be about 15 micrometers for a fibroblast cell. So the way we began by doing this is on the right-hand side, the equations, basically we found the maximum force that our system would be experiencing at any time during normal operation, which happened to be when static friction was being broken when pistons began moving. So we multiplied the weight that could be the maximum weight seen by any of the actuators, which came out to 75 grams, by the gravitational constant, by the coefficient of friction between the acetyl bushing and the stainless steel rail, to find a maximum force. We were able to take that force and divide it by the piston area to find a pressure that the system would be running at. So from that, we were able to treat the fluid supply lines as a thin wall pressure vessel. And by doing that, we were able to find the diametral strain that would be experienced along the hoop direction, using the pressure and the radius and the thickness that we had from the lines. And so from that, we were able to find the amount of diametral deflection and actually use that to find the expansion area of the lines. So by multiplying that by the length of the lines, we were then able to find a volumetric increase within the supply lines due to expansion, and use that to find a positional accuracy of approximately 7 micrometers. We also calculated the hoop stress, which was important to make sure that our lines weren't going to be rupturing before they became disconnected from the barb fittings, because that could lead to a worse failure mode. So moving on, the calculation on the bottom, we also needed to find the print head tolerance due to the linear actuator step size. So in order to do that, we estimated the step size to be approximately 1/10 of the smallest of the actuator repeatability from the spec sheet, which we found by looking at multiple spec sheets of linear actuators. And then we multiplied that step size by the ratio of areas between the driven piston, which was the glass syringe in the control box, divided by the driven piston in the actual assembly. And so by doing that, we were able to find a tolerance, again, under 8 micrometers, approximately 7.7. So even when we add these two tolerances together, because they're going to be acting in the same direction, we're still under that 15 micrometer tolerance that was given by the customer needs. So additionally, we wanted to make sure that we weren't going to be running into any kind of thermal over temperature within the control box. So we performed a convection heat transfer analysis. So to determine our heat generation that we would be experiencing, we used thermal efficiencies of 75% for our linear actuators and our case fan power, or our case fan. These were conservative values so that we would tend to get a temperature on the higher end of the spectrum to ensure that we were within our allowable values. Additionally, we added in the control power for our smoothie board to determine the total heat load that could be generated. And then from that, we looked at the specs for the case fans, and we found the volumetric flow that could be expected through those case fans, assuming that there would be no significant flow choke due to the size of the inlet cutouts for the PUP logo on the front face. So from that, we were able to find the cross-sectional area of our control box and determine the velocity of the fluid flowing through that box. Once we had that value, we were able to find multiple dimensionless numbers, including Reynolds number, Prandtl number, and Nusselt number, which allowed us to calculate, a heat transfer convection coefficient and ultimately solve our heat transfer problem, where we found that our temperature was in fact under 100 degrees Fahrenheit, which was the temperature range that we were aiming for. Because on the lower end of the spectrum, we found that some electronics tend to decrease their performance around 120 to 140 degrees Fahrenheit. So we felt that 100 degrees Fahrenheit was a reasonable temperature goal, which was in fact only a temperature difference of 18 degrees Celsius above our ambient.
So as we mentioned before, the design is based mostly around off-the-shelf parts, and the majority of our BOM costs went towards the actuators and syringes, since there was 4 of each, and some other components that were also large contributors to the cost were the modified turret mount, the Smoothie board, and the cooling fans. The remainder of the custom parts, such as the one seen below, they were either designed to be made on manual lathes and mills, or for the more complicated parts, like the driven and driving components pictured, they were designed for basic 3-axis CNC milling. And to quote the parts, we used a feature-based quoting system at a standard shop rate of $90 an hour. And the quote takes the tightest tolerance into account and required operations. So if you have a part that's going to require multiple setups or different machines, that will all be reflected in the manufacturing cost. And for assembly, the design was made to try to make the assembly process as repetitive as possible. So for example, with the syringe system, there are 4 identical ones for X, Y, Z, and dispensing, along with the pistons and linear rods. So by making every subassembly unique in that aspect, we're able to make it easier for the assembler or the microscope technician to put it back together, because they can follow the same diagram for all the assemblies.
So why choose PUP? Our design is under $4,000 and it's expected to last 5 years. You don't require any specialized tool to actually assemble our design. Our design is designed to have fast manufacturing, and repeated parts and high OTS parts support the quick manufacturing process. Thank you, Northrop and Cummins, for your continued support of our capstone program and making our program the best in the world.
All right. Great presentation. Thank you for sharing your design with us. Do we have any questions from our gallery?
How did you determine a 5-year lifespan?
It was determined by our customer, and we calculated the life expectancy of the linear actuators, and it is expected to last around 5 years.
Other questions?
I just want to chime in real quick. I had the privilege, I guess I can call it, of doing a design review with these guys back a couple weeks ago. So I just wanted to say, guys, I really appreciate you took the stunning majority of my advice to heart with some of the tweaks and changes that you made. So, you know, I appreciate you guys having that chat with me and, you know, acting on some of the criticisms. So instead of digging your heels in and saying, no, we're the best. So it's a, you know, it's a good trait to have. So
yeah, definitely appreciated your input.
It was a fun roast. Now you guys, you know, get some slack for me this time around, because I already roasted you once 2 weeks ago.
Okay, you said you had glass pistons. the environment that you know this is going to be used in is lab environment, and people are probably used to working with glass hardware. But is there any safety concern, any concern with like water leaks getting into electronics if something breaks in there? What are kind of the safety aspects here?
So the linear actuators bottom out before the piston bottoms out. So we're not worried about like any mechanical failure on the glass syringe due to like like pushing of the system. Our like most likely failure mode would be the like bursting of, or not the burst, but the disconnect of the line from the barbed fittings. So that potentially like induces a hazard there that could be avoided with pressure sensors on the lines themselves. So as like a shut off for the system. But that's why we opted for the water opposed to a conventional hydraulic fluid for pushing the system around, is to avoid some of those hazards. Most likely it would disconnect from the barb fitting on the printer side itself, not in the control box, due to the fatigue and the moving around of those lines. But yeah, that is like ultimately the biggest risk is like dumping water like over your experiment or on your table. If that answered your question.
Yeah, thank you.
Okay, we've got time for one more question, and then we'll have to wrap up. So if anybody has the final question, now's your time. Anyone else? Okay, so seeing no additional questions, I think we'll wrap it up there. So yeah, Dan Prestridge writes, "Great job, y'all," in the in the chat. So let me drop into, there we go. So in the chat window now, this is the URL for those of us who are just joining us. This is the URL that takes you back to the agenda for today's events. And so if you go back to that agenda, you'll be able to find a link, Zoom link to the next presentation, which is the one that's meant to start at 10:30, which is group 2, Bellow 0. So we'll convene there in just a second. And I did want to just remind all of our panelists who are doing evaluations to please continue filling out your grading rubrics so that we have some assessment data that we can share with these students and give them some feedback on how well their presentations went. So with that, we'll wrap it there and see everybody.
Just one real quick note. There was an error with the MEC 3 presentation links on that page that I fixed this morning. So if you've had it open and you haven't refreshed the page, refresh the page at some point today before we get to the MEC 3 presentations at the end. So we can all wind up in the right spot.
Okay, sounds good. Yeah, we should remind everybody of that at the end of every presentation.
Yeah.
Okay, so we'll see everybody in just a moment in the next presentation. Thanks to the putt printer guys for sharing your design with us. It was excellent, awesome, especially if Dr. Nemi had nothing to roast you about. All right, so we'll see it.
Yeah, thank you everyone for coming and being here for the presentation.
All right, excellent job. Thank you.